question 11 is a bit of a step up in difficulty because this is not a standard cycle. It's not just a simple combustion cycle with combustion products forming the link, or a formation cycle with elements forming the link. We've got different combinations of reactions. So let's first of all just see if we can understand where this cycle comes from that they've put together. So the mission is to calculate this number, the enthalpy change for reacting barium and oxygen, the elements, to form barium oxide, the compound. So that's the enthalpy change of formation of barium oxide, and that's what we're trying to find using this method. Now the numbers it gives us are for reactions which turn this into barium hydroxide and this into barium hydroxide. So you might first of all be tempted just to put barium hydroxide at the bottom here, but actually it's not going to be quite as simple as that, as we'll see in a minute. So what we're going to do is to separately put those two reactions on. So we've got this one going to form barium hydroxide. So we've got delta H for barium reacting with water to form barium hydroxide plus hydrogen is minus 560. Now the problem is that in order to do that we have to put two H2O's in, because you know, that's what we need to balance the equation. So that means that we'll have to add two H2O's here. But in order to keep it balanced, if we're adding two H2O's on this side of the equation in order to make the reaction to form barium hydroxide possible, we'll have to put two H2O's on this side as well. Okay, so that's just, they've got to be there to keep it balanced. And in the context of this reaction across the top, it doesn't matter, because the two H2O's are there at the beginning and they're still there at the end, so they didn't change in any way. So it's not, they're not going to influence the fact that that's the delta H of formation of barium oxide. It just looks a bit weird because you think, what are those waters doing there? But so long as they haven't changed, you just cancel them out and say, right, that's irrelevant, that's just the delta H of formation. But the waters have to be there for this reaction. And you can see, looking at that equation, that that gives barium hydroxide, but it also gives hydrogen. So we have to put hydrogen down there. And it's still not balanced, because what about this oxygen? That wasn't involved in this reaction. We needed that for this reaction, but it wasn't involved in this one. So again, it's got to remain unreacted, just like the waters did going across there. This oxygen wasn't involved in the reaction of barium and water, so it just gets carried through, so we get a half O2 down here. Okay, so the actual reaction there doesn't involve the oxygen, so you just ignore that for this because it's unchanged, and you have barium plus two waters goes to barium hydroxide plus hydrogen, so that's this one, and therefore delta H is minus 560 going across here. Now if we do the same thing coming down here, again to form barium hydroxide, and the equation is barium hydroxide plus water, so barium oxide plus water goes to barium hydroxide, but you can see at the moment we've got barium oxide plus two waters, because we had to have those two waters there to balance those ones out, but this is only reacting with one of them, so one of those waters has got to be written in here, just to keep it balanced again. Okay, so overall, the change there is just barium hydroxide plus one water gives you, barium oxide plus one water gives you barium hydroxide. So that reaction, but there's one extra water that's just being carried across and isn't involved. So once that's cancelled out, you can see that's the same reaction, so that's minus 211 going that way. Now if we look at what the connection is between these two things at the bottom, you can see that you've got barium hydroxide aqueous in both cases, so this time that's not changing, and what's changing is that you've got H2 plus a half O2 there, and you've got water here. So of course H2 plus a half O2 going to water is formation of water from its elements, so that change is just delta H of formation of water. It doesn't look like it at first sight because you think, yeah, what's all that barium hydroxide doing there? But you can see the barium hydroxide didn't change. So you just cancel it out and say, right, what's left is H2 plus half O2 goes to H2O. So that's delta H of formation of water, which is minus 286. So now, finally, you can see where Hess's law is going to come into play, because we're trying to calculate this number. Okay, delta H of formation of barium oxide, and by Hess's law we can go on a 3-stage journey this time, like that, down, across and up, which has the same overall effect as that. So the sum of those 3 steps will equal that one, which is what we're trying to find. So the first one, well, that's the same as this, because the arrow's going in the same direction, so that's minus 560 kilojoules per mole. This one is the same as that one, so that's minus 286. But the third one is going the wrong way. Okay, it was minus 211 going to form barium hydroxide, but we're unforming it, turning it back into barium oxide, so it's plus 211 going that way. And so that gives us our answer, that delta H of formation of barium oxide is equal to minus 560 minus 286 plus 211, and that equals minus 635 kilojoules per mole, which is the answer. So that seems quite a scary question compared to the previous ones, but when they give you non-standard cycles like that, they will generally give you help like that in seeing how the things have to string together. So don't be too fazed by that, because you saw in the question that it gave you most of the cycle and you just had to figure out what was going on with it. But I think it is important to understand why, for example, this reaction across the top doesn't look like what you expected for the equation for formation of barium oxide. You think, what are these waters doing there? And it's important to realise, first of all, that they don't matter because they're unchanged. 2 waters on the left, 2 waters on the right, so who cares? They're not changed, so they don't affect the delta H. But they had to be there in order to make this reaction possible. And indeed this one as well, at least one of them had to be there for that one. So it's clever the way it all fits together, and make sure you can try and understand that. But in the end, also make sure you're not scared by these questions, because they will give you help with a complicated cycle like that and just expect you to finish the story off, as was the case in this one. The first part of question 12 is a recap on MC delta T, but it's done sort of as if it were an experiment rather than just giving you the numbers. And this is something, again, you have to be ready for in the exams. That because you don't have a practical exam, they will set questions like this which give you data as if you had measured them in a practical, to see that you do know how to handle them. So the first thing you need to get from this is to realise that you need to know how much KHS reacted, and you need to know what the mass of the solution at the end was, and you need to know those in order to calculate delta H for the reaction. So if we look at these first 2 measurements, this is just the beaker and the cup. Okay, so the idea is that you have a setup like this, and you do that. So this is the beaker, and that's the cup, and you do that partly to stop the beaker from falling, to stop the cup from falling over, but also it provides a little bit of insulation because you've got a sort of dead air layer there, which will help to insulate and reduce heat loss. So that's the setup. So that's the beaker plus the cup, and we've also got the beaker plus the cup plus the KHS. So you have this, but now with a bunch of stuff in the bottom. Okay, so this is 136.24 grams, and this is 134.74 grams. And you can see the difference between the two is just the KHS, this solid in the bottom here. So we get that the mass of KHS is 136.24 minus 134.74, which is 1.50 grams. Not just 1.5, that's important, because remember, when you're dealing with experimental data, if it's a mass and it's been measured to 2 decimal places, when you do the subtraction, you should still put the 2 decimal places down. So if you had just written 1.5, you would have lost a mark. It wouldn't have affected your final answer, but you would have lost a mark in terms of recording the information. So if masses are measured to 2 decimal places, then when you subtract them, you still know them to 2 decimal places. So that's what they must be recorded to. Now what about the solution? So the idea is that you then have this stuff and you add the acid into there. And what that gives you then is, here's your beaker, here's your cup, and now you have a solution that's formed, and the gas escapes into the air. So that's what happens once you add the acid. And so we need to know the mass of the solution at the end, and we can get that because, again, it's just the difference between this and this, right? Because that's the beaker plus the cup on its own. That's the beaker and the cup with the solution in it. So it's this final mass, which is 184.94 grams, minus just the empty beaker and cup. Okay, so the mass of the solution is 184.94 minus 134.74, which is 50.20 grams. Okay, and again, not just 50.2 but 50.20 it should be, because you've measured it to 2 decimal places. So the other number we have to calculate is the temperature rise, and obviously that one is easy. You just get that by subtraction of the initial temperature from the final temperature. So you get that delta T, the temperature rise, is 24.5 minus 19.5, which is 5.0. Again, not just 5, but 5.0 degrees C. Okay, so now we can use those numbers, and it asks us first of all to calculate the energy change for the reaction. So that's just Q. Okay, so this is now part A, which is that Q is mc delta T. Let's remember the method. And M is the mass of the solution. Now in most of the examples you've done, we've worked that out by assuming that the volume of the solution in cm cubed is equal to the mass in grams, because that would be true for water and is a reasonable approximation for an aqueous solution. But here you don't have to do that because we've got the actual mass of the solution, which is 50.20, so that goes in there. Times C is 4.18 as always, which is the specific heat capacity of water, and again you always use that for aqueous solutions, times delta T is 5.0, and if you crunch those numbers you get 1049 joules is the answer for the amount of heat transferred. And sooner or later we're going to need to turn that into kilojoules, so we may as well do it now. So divide by 1000 equals 1.049 kilojoules. The next thing we need to know is, in part B, the amount in moles of KHS. So that's easy because we've got the mass of KHS, so we just get moles of KHS is equal to mass over MR, which is 1.50 divided by the MR adds up to 72.2, and that gives us 0.02078 moles. Okay, so now we've got the heat transferred and we've got the moles, so we can now calculate delta H for the reaction. and it will be negative because the temperature went up, so it's exothermic. Remember, if the temperature goes up, it's exothermic, so the sign is negative, so it's minus Q over moles, which is minus 1.049 kilojoules divided by 0.02078 moles, which comes to minus 50.5 kilojoules per mole. Okay, so now we have enthalpy data for two reactions. This one, which we've just calculated, so KHS plus HCl, we've got minus 50.5 kilojoules per mole, and then in the question it gives us delta H for this second reaction, K2S plus 2HCl. And it's asking us to combine those data to find delta H for this reaction. Okay, so that's our objective. So this is about putting a cycle together again. Now again, in the question it kind of gives you the cycle, but I think it's helpful to understand what's going on here if we just try and work this out for ourselves. So we think, right, what we have is two reactions, both of which give you KCl, and so it's fairly clear that what's going to make the connection at the bottom is KCl. So if we look at the first reaction, KHS plus HCl, you can see we've got two KHS's there, so we're going to have to put two HCl's in here to react with those, and that will take us down here to give us 2 KCl aqueous plus 2 H2S. Okay, and delta H for that reaction will be minus 50.5 times 2. Right, because when 1 mole of KHS reacts, it's minus 50.5, but we've got 2 moles reacting, so it's minus 50.5 times 2, which is minus 101 kilojoules per mole. Now if we look over here, what have we got? We've got K2S plus an H2S. And we've got an equation for K2S, again being converted into 2KCl. The H2S, you can see, is still there at the end. It's just being carried across. So just like we had in some of the in some of those instances in question 11, you can have something which is there at the beginning, still there at the end, and is carried across. So if we ignore that H2S and one of those H2S's, you can see what's left is K2S being converted to 2 moles of KCl plus 1 mole of H2S if we add 2 HCl to it. Okay, so that change, one of the H2S's is just being carried across, so we can edit that out and we get K2S plus 2 HCl goes to 2 KCl plus 1 H2S, which is that reaction, and therefore that's minus 74. And having constructed that, we're in good shape to apply Hess's law, because it's now a very simple one where we say, right, this is the one we want, and Hess's law says we can do it in 2 steps like that. Okay, coming down here and then up there. First leg is the same as that one, so that's where I missed the minus sign off there. So that's minus 101 coming down here. This one is the reverse of that one. It's minus 74 going down, so it's plus 74 going upwards. And so we get that delta H is equal to minus 101 plus 74, which is minus 27 kilojoules per mole, which is the answer to the question. Now that cycle looks more complicated than the one which was given to you in the question, but you can see that all they did there was basically to leave these 2 HCl's out of it, because you've got the same thing being added on both sides. So it's the same as we do in combustion cycles, where we don't bother showing the oxygens on both sides because they come out in the wash. The same applies with the HCl here. But if you found that confusing in the question, hopefully seeing that full cycle, you can see that that makes more sense. Questions 11 and 12 are definitely harder than other ones, so don't panic if you find these too difficult. Focus mainly on getting the more standard ones sorted out, because they don't often give you more complicated, less standard cycles like this, and when they do, they generally give you a lot of help. So it's good to spend some time seeing if you can get to grips with them, but if you still feel a bit shaky on them, as I say, don't worry, that's not the main priority in this topic.